learn how to take derivatives using logarithms. And in order to do this, we'll have to remind ourselves of some properties of exponents and logarithms. So let me go over those just briefly. So over here in this column, I have some properties of exponents. When you're adding exponents, you're actually multiplying expressions. When you subtract exponents, you're dividing expressions. And when you raise something with an exponent to another exponent, you're multiplying those exponents. And the counterparts of those properties are over here with logarithms. If you're summing the two expressions that involve logarithms, you can unite them with multiplication. If you're subtracting two logarithmic expressions, you can unite them with division. And then if you're taking the log of something to another power, you can bring that power out in front and make it a multiplier. And we're going to be using this property a fair amount in the next few minutes. So what logarithmic differentiation allows you to do is take the derivatives of things that have variable exponents. So the example I'm going to do in a moment here is y equals 7 to the x. Now, it's tempting to use the power rule to take the derivative here because you see a power. But because the power here is not a constant, so because it has a variable, we can't use the power rule. If that exponent is a number, positive, negative, fraction, decimal, you can use the power rule, but it has to be a numerical value. Once the exponent is a variable, then you have to look for another method. And the method we're going to use here is called logarithmic differentiation. So what we're going to do first is we're going to apply logarithms to both sides of the equation. And that will allow us to bring that exponent down. So here's the original equation. And then underneath it, I took the logarithm of the left and got ln of y. And when I took the logarithm on the right, I got x ln 7. And the whole purpose for doing this is to get that x down on the ground so that we can work with it. And now we're going to take the derivative of this equation. And the derivative on the left is 1 over y dy dx. That's just the chain rule. And on the right, x times the ln of 7 is x times a constant. And the derivative of x times a constant is just the constant. So there's the derivative equation. We'll clean it up. We'll bring y up to the right-hand side. And then we'll replace y with 7 to the x. And then there is our derivative. So the derivative of 7 to the x is 7 to the x ln of 7. So we get back the function we began with, but we have to multiply by the natural log of the base we're using. And if we had done this same problem, but with 2 to the x instead, we would have gotten 2 to the x ln 2. If we had done the derivative of 9 to the x, we would have gotten 9 to the x ln 9. So you can really take derivatives of exponential functions in any base. And it would even work if we did it for e to the x. The derivative of e to the x following this model is e to the x ln e. But the ln of e is the ln of e to the first, and ln and e undo each other, so that just equals 1, and we get e to the x. So it even works with what we're familiar with, that the derivative of e to the x is e to the x. And just a quick aside, looking the other direction now, suppose we had to integrate 7 to the x dx. Well, we would get back 7 to the x, but instead of multiplying by the natural log of 7, we would multiply by its reciprocal. Because when you integrate, you introduce reciprocals rather than just multiplying factors. And then I would have a plus c at the end. And if I were integrating, say, 9 to the x, I would get 9 to the x with a 1 over ln of 9 in front, plus a c. All right, so why don't you try one that's a little bit more complicated. Try to do the derivative of f of x equals 9x squared. You could pause the video and then turn it back on in a moment. I'll go ahead and go forward now, assuming that maybe you've already done it yourself. So I'm going to begin with y equals 9x squared. I'm going to apply the natural log to both sides. Whoops, that x squared should be in the exponent, but I'm just going to write it down here as a multiplier now. And I'm going to get the natural log of 9. And then I'm now going to take the derivative. And I get 1 over y dy dx equals, and then I'm going to get 2x ln of 9. And then I'm going to bring y up as a multiplier, but I'm going to, instead of writing y, write 9x squared. And there is my result. Notice that I got back the original exponential function, I got back the derivative of the interior function, and I have the ln of the base I was working in. And the 5 to the sine of 4t would work in a similar fashion. So in number 2, I comment here that you could apply logarithms to these other functions, other types of functions that we've been working with. You wouldn't want to do that, but even if you were to apply logarithms to these equations and then finish taking the derivative using logarithms, you would end up with the equivalent results. So here you would still end up with 2x. Here you would still end up with e to the 7x times 7. And here you would still end up with 1/2 t to the 5th plus 1 to the negative 1/2 times 5t to the 4th. So, all right, let's make things a bit more complicated now. What happens if the function you're differentiating has not only a variable exponent, but a variable base, like x plus 1 to the x? Well, we're still going to apply logarithms. We want to get that exponent down. So you apply logarithms to the entire equation. You get the ln of y over here. X comes down in front, and you get x ln of x plus 1. Now we'll take the derivative over here using the chain rule. We get 1 over y dy dx as we have before. On this side, this is a product, x times ln of x plus 1. So we have to use the product rule. So u prime v will be 1 ln of x plus 1 plus u, which will be x, and then v prime, which is 1 over x plus 1. So I use the product rule here to express the derivative. And that was because I have an x times something else involving an x. And then, like before, we'll bring up y as a multiplier. So I'll put y in front of that sum, and then I replaced y with what it was representing, x plus 1 to the x. So here's the original function, and then here is the result of having used the product rule. And it's a long expression for the derivative, but it is accurate. So why don't you try this example here? You could turn off the video or pause the video and then start playing it again, and you can see my solution. So here I go. So I'm going to start with y equals x to the sine of x. I'm going to apply logarithms to both sides. And that allows me to bring that exponent down in front. And now I'm going to take the derivative. And on the left, I get 1 over y dy dx. And on the right, using the product rule, I get u prime v plus u v prime. And then my final step, I'm going to bring y up as a multiplier, but instead of writing y in front, I'm going to write x to the sine of x. And then maybe I'll put everything else in a bracket. So I'm going to get this long expression. So I get back the original function, but then I have here the result of the product rule. In a number 4, I ask you to generalize your work. So let's now work with just general functions here, f of x raised to the g of x. So we'll apply logarithms to bring that exponent down. And then I'll take the derivative on the left using the chain rule, the derivative on the right using the product rule. So there's u prime, here's v, plus here's u, and here's v prime, 1 over f of x times f prime of x. And then the last thing we have to do is bring up y as a multiplier. That should be dy dx there. And y is f of x raised to the g of x. And then I would multiply by all that stuff. I guess I'll go ahead and write it. So all that stuff is sitting inside and being multiplied by our original function. So that's how you handle taking derivatives of expressions that contain a variable exponent. Now there's some other kind of interesting things that occur when you work with logarithms. They can come in handy if you have to take the derivative of a real ugly mess that you can re-express or split up using logarithms. So for example, if we were to differentiate this expression right here, under normal circumstances here, we would have to use the power rule and the chain rule and the product rule and the quotient rule. It would be a big mess. But before we do that, we could apply logarithms and split this mess up. So, for example, I could take the natural log of this equation, and I'll have ln of y over here. And then each of these terms, when I take the natural log, I can bring down the exponent of 1/3 and put it in front. And then I can split this product into a sum, and then split the quotient into a subtraction. So I'll end up with 4/3 in front of ln of x minus 5. I'll end up with 7/3 in front of ln of 2x plus 3. And then I'll end up with minus 8/3 of the ln of 5x plus 8. So I haven't done any differentiating yet. I've just rewritten this using logarithms to create easier things to differentiate. And now we'll take the derivative. And the derivative on the left is 1 over y dy dx. And the derivative on the right, using the chain rule, all those ln expressions will end up as quotients. And then I have to multiply by the derivative of the interior. So there they all are. And then I can bring up y as a multiplier, and then I can replace y with what it was representing. So here's the original function, and then here are the derivatives of all those other pieces. So and that's a more elegant way to express the derivative of this mess than using the power rule and nesting it with the chain rule and the quotient rule and the product rule. So you probably won't see something like that. I just thought I'd share with you that it's a nice technique that you could use if you ever were to see something like that. So, and I'm going to suggest that we not do number 5 for the time being. The last thing I want to show you is that you can use this property to verify the product rule and the quotient rule. And I'm going to do the one just on the left. I'm going to show you the product rule. So y1 is the product of two functions. And what we're going to do is apply the natural log to both of these and see what happens when we continue and differentiate that way. So I've taken the natural log of both sides, so I have the ln of y1 over here. And then when you take the natural log of a product, you can split it into two natural logs. And now we'll take the derivative. So I'm going to get 1 over y1 times dy1 dx equals, and then the derivative of that is 1 over f of x times f prime of x, and the derivative of that is 1 over g of x times g prime of x. And now I'm going to multiply both sides by y1, so now my derivative equals, and when I put y1 out in front, it's just f of x times g of x. And then inside here, what I'm going to try to do is add these two fractions. And they need common denominators. This one needs a g of x, so I'm going to multiply the top by g of x. And then this one needs an f of x, so I'm going to multiply that one by f of x. And then the common denominator is f of x, g of x. And then something really nice happens at this point. This product here cancels with that product down there. And what we're left with here is the product rule. So the derivative is f prime g plus g prime f. And if we had done something similar to that using the quotient rule here, we would have gotten the quotient rule version of using logarithms that we would have gotten if we had worked with the traditional quotient rule. So I hope that was insightful. The big takeaway, though, is that if you see a variable and an exponent, apply logarithms, and that allows you then to take derivatives more traditionally.